Okay. Okay. There she is. There they are. There they. Okay.
Good
Okay.
morning.
Good morning. Oh, with the triple. Okay. So good morning, Gabriella. Good morning, Jocelyn. Good morning, Sydney. Good morning. We are in. Wait, hold on.
Morning, Professor.
Oh, and that was a Muhammad. All right. That's the double. That's and he's coming. Wait. Okay. And that's Sydney. And good morning, Effie. Good morning, Norma. Good morning, Melanie. Good. Oh, more people. Sorry. What did I say? Jocelyn's got glasses. I like the glasses. Sorry. Did I say? Oh, more people. Okay, okay, okay. Okay. And Chanel, good morning. Teresa, good morning. Okay, I'm still confused with the word. Sorry, I'm in a different place. Um, right. And now the chat. Okay. Good. Good morning, Sinead. Good morning, Effie, for the double. Good morning, Mohammed, for the Wait, what did I have? Yes, for the triple. Good morning. Good mornings, Teresa. I like. Okay, I'm not gonna, but yes, it's a we program. Okay. Good morning, morning, Christopher. Good morning, Jocelyn, for the triple double glass. Yes. Oh, there's Lunar. Okay. Good morning, and it's full. Of course, that makes sense. Yes. All right. That's good. We should really, yeah, come by some. We should really talk about that. I'm sure you. Okay. Anyway. Good morning. Melanie for the double. Good morning, Genesis with the exclamation point. Good morning, Lunar for the double. Okay, we got that. Okay, okay. Let's just get straight to. I want to get straight. Well, I'll show you exactly where we are. So yesterday, I want to get specific now. Yeah, pardon me. Like I get very excited about the integral. I really do. I love integrals, but a quick thing. Why part of the reason I love integrals is because I love the fact that I don't hate them anymore. Just to be, I mean that you right to the extent that physics class um is mass healing for the math traumatized among us. I mean integrals scare. First they scared me, then I just avoided them, then I hated them, then blah blah blah, then I repressed them, but eventually. I grew, and they're still very hard, but I love integrals now because of what they mean, blah blah blah. But now, so that was my whole trying to get you to appreciate them Monday. But now, of course, I want to get specific. Um, um, I want to apply an integral to a fundamental principle of physics. That's what we're going to do, and that is to say. That is to say, I'm going to do a screen share here. Wait, someone's here. Sorry, sorry, sorry. Just to tell you where we are. So we're going to be specific and concrete and tethered to the homework today, which of course works better for some of you. Some people like the theory, some people like just like dealing with homework problems. I understand that. So we do both. So here I'm trying to do the screen share. So what I um where to go, where to go. So what we're doing right now is this, like literally this. Yes, this. Um Which means I want to, okay, I want to step back and explain. Well, yeah, so I want to do this. This is all about springs. Really, this is about elasticity. That is to say, this problem is about a spring, and the physics of a spring. But really, like we always do in physics, we're studying a spring to really understand what it means to be springy. Like anything that we say about an individual spring is really what we're saying about the property of elasticity. A material that we regard as elastic is a material that we think of as being made up of lots and lots of little springs of this nature, even if perhaps they might be atomic springs, right? They don't necessarily have to be coils of metal in order for them to demonstrate the property of elasticity. So what this problem is all about is what does it mean to be elastic? Okay, so we're going to solve this problem, but I'm going to now switch screens again and tell you exactly what I think it means to be elastic. I'm going to switch screens again. I'm going to switch screens again. Hold on. Here we go. Here we go. Okay. Okay. Well, so the here we are, here we are. Oh, good morning, George. Sorry. Um, so to cut to the chase, well, I'm not going to. The top equation right here on the board is what is known as Hooke's law. It, it is the law that governs the behavior of any well-behaved spring, or put another way, it is the law that defines what it means to act springy. So, and then we're gonna integrate that law in order ultimately to calculate the work done by a spring. Because remember, because the whole point of Monday's class, is that um, work is the integral of force with respect to displacement. Um, so, um, so we're going to take the force exerted by a spring and integrate it in order to see what kind of work the spring does on the mass in this homework problem, and ultimately, therefore, to see how the spring transfers energy um, of the mass. So, okay, this blue thing is supposed to be a straight line. Um, okay, just oh, sorry, I'm looking at the chat. Got it, got it. Thank you. Appreciate the opponent. Hold on. Okay, yeah, got it. Direct chat person. Okay, thank you. If I have a spring, so imagine there's like a tightly long coil of metal, and say one end of it is fixed to a wall, or to some rigid position, and the other end like has a mass at the end of it that can be moved back and forth freely. So I try to hold the mass on this one end of the spring. There's a certain position that we call the equilibrium position, that we call x equals 0. There's a certain position where the mass will just eventually come to rest or just sit there. A certain position where if I place the mass at that position, it won't have any inclination to move from that position, right? I mean, I think that's intuitive. There's a spring has one orientation where it's relaxed and stable. But if I try to pull the mass out a couple of meters from that position, or even if it's a good symmetric spring, or even if I try to push the mass in like a piece of gym equipment, a few meters to the other side of the equilibrium position, it becomes difficult to hold the mass there, right? Some force is required for me to hold the mass at any position other than the equilibrium position, right? Which implies, well, which means if you did a free body diagram and did F net equals ma, it means that the spring itself must be exerting a force on the mass directed so as to restore the mass back to the equilibrium position. So far, I think what I'm saying I sort of believe you all kind of know this or could picture it somewhat easily. Obviously, stop me if you can't. So a spring exerts automatically a restoring force on its end, on any object affixed to its end. It exerts a restoring force in an attempt to bring the mass toward equilibrium. If the mass is to the right of equilibrium, the spring will pull to the left. If the mass is to the left of equilibrium, then the spring will pull to the right, right? So, so hence the negative sign in the equation that I'm about to restate. The force is always directed in the opposite direction from displacement from equilibrium. The force is always directed in the direction opposite to displacement from equilibrium. That's what we mean by a restoring force. Okay, so but here's the key. The thing that's interesting about the restoring force exerted by an elastic material is that it's directly proportional to displacement from equilibrium, i.e., when the mass is just sitting at equilibrium, there's no force exerted at all. If you pull the mass out like a meter from equilibrium, there will be a certain force trying to bring it back. If you then try to hold the mass out at 2 meters from equilibrium, you have to sweat twice as much. You would find that the force exerted by the spring is twice as intense if you bring the mass out to twice the displacement, and so on and so on, right? In other words, this graph, if we were to try to plot force as a dependent variable in its response to displacement as an independent variable, we would find not just that as one goes up, the other goes up in value, in magnitude, but in fact that they go up in the same at the same rate all the time. It's a straight line. It's direct proportionality. That is a discovery. That now, by the way, it's not a perfect discovery. As you start to stretch a spring more and more, or and other things like that, the law sort of starts to get less and less perfectly true. And if the spring is not very long to begin with, the law won't be perfectly true. Like the spring has to sort of obey some pretty tight conditions to make this approximation pretty accurate. But it's not hard to find springs that do obey those conditions. So the idea of Hooke's law is that a spring or all elastic materials exert a restoring force that is opposite to the direction of displacement from equilibrium, but directly proportional in magnitude to the displacement from equilibrium. Hence, force to displacement can always be plotted as a straight line. And strictly speaking, it's in the fourth quadrant, not the first quadrant, because as the magnitude of as the displacement gets bigger, the magnitude of the force gets bigger as well, but the direction is always opposite. So hence, the line goes down rather than up. That's the first point of this graph, is it's saying that Hooke's law, what it means to be elastic is to exert uh, a linear restoring force. Now, so this is one of those many things in physics that's like hopefully clear and said, like when you say it, it almost seems like, okay, that seems so logical. I'm either missing something or I don't even know why it needs to be said. Well, contrast, like this is not the way we understand gravity to be. Like there is a similarity between springs and gravity in that gravity likes to bring things to the ground. If you bring something above the ground, if you bring a mass above the ground, and gravity will try to restore the object to the ground. In that sense, gravity seems like it's acting kind of like a spring. It's always trying to bring things back to the equilibrium of zero height. However, the force of gravity is mg, right? As far as we know, it doesn't. If I try to hold something here, it's no less difficult apparently than holding something here. If we were to make a graph like this for gravity, we would have a horizontal line, right? So gravity is a constant force elasticity is a linear force. And you might want to put that in your notes or something. Like the main point I'm trying to make right now. The main reason we're now moving our focus to springy materials is it's our first opportunity in physics to look at a sort of common, recognizable, easy to work with, predictable force, like a force that's as common and predictable and easy to work with as gravity, right? But a force that in fact varies as a function of position, right? It's not a coincidence that this is coming up today or it came up in this homework, right? Because this is like now the Sisyphus example from Monday. Springs automatically, like, so the reason we cared about gravity so much in physics, and we do forever, we care about gravity, but the reason it comes up early in a physics course is gravity provides a ready, natural example of a force and therefore an acceleration that's constant. So when we're doing all of our constant acceleration equations, blah, 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 gravity is like this great example for that. Now we're moving like one step up the math food chain and going, instead of horizontal forces, we're going to linear forces, most vividly demonstrated by elastic materials. Okay, so that's like that's the connection here. So when we look at a spring, we're looking at something that gets stronger and stronger as you get farther and farther away from equilibrium. That's a new idea, and it requires the math that we talked about on Monday. Okay, so that's why we're going to do it. There's one other thing I want to, and stop me if I'm sorry. I'm like also the new Zoom thing. Sorry, it's like the camera adjusts. Sorry, it's like a little freakish. Um, 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 um. There's one other thing I want to say about this graph, and these notes. Straight line means constant slope, right? Okay, so and slope is rise over run. In a graph like this, like the rise is force, the run is displacement. So rise over run would be like, F2 minus F1 over X2 minus X1, like the change in force divided by the change in displacement. Well, the slope of this graph is what we call K for any given spring. That is, sorry, why is this? Like I'm saying, any spring you would ever play with in the lab, and that when you start physics 204, see you in a month. Like one of the first, no, the first lab you do is totally like playing with a spring. Okay, it like picks up where we're like leaving off here. Um, when you play with a spring in the lab, any given spring will exert a certain amount of newtons of restoring force for every meter of displacement. But not all, right? But some springs will exert more newtons for every meter of displacement than others, i.e., the graph of any spring will always be a straight line, but some of them will have steeper slopes than others. Physically, a steep slope means the spring is, you have to pull the spring really hard to hold it still, even at 1 centimeter. That slope, that property of springs, we call K, and K measures the stiffness or the strength of the spring in, of course, newtons per meter, if you see what I'm saying. So from now on, when I say Hooke's law is F equals negative Kx, that means for any given spring, it'll exert a certain number of newtons per every meter. That newtons per meter constant ratio is what is known as K. K is a physical parameter that describes any spring. Like you can measure it in the lab, and you do at the beginning of Physics 204. Or once they make a spring, they could put it in a box, and companies could write on the box, K equals 200 newtons per meter for this spring or whatever, and that's telling you how strong it is. Okay, so that's the math and the physics of this. So now we're going to apply it. I'm looking at the chat. Okay. Now we're going to apply it to the homework. Let me just switch the view on the screen. Hold on. Right. Okay. So we have this. And sorry, if someone could remind me. If someone could remind me in the chat, I think this is homework 8, but I always get confused. It might be 9. Sorry. Homework now. Thank you, thank you. Thank you, Mohammed, and thank you, direct chat person. Awesome. 9. All right, sounds good to me. Okay. Wait, I just oh sorry. Okay. 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 So, right. So here's the fact. Here's the diagram. Here's the numerical fact. So the spring starts off, it's being held at a position that is not equilibrium. Again, wherever equilibrium is, we define to be x equals 0, and then any displacement from that. And we should be defining a coordinate system. Like in this case, it seems like we're saying this way is plus, i.e., when we extend the spring, we're calling that positive. When we compress the spring, we're calling that negative, et cetera, et cetera. So it gives you these facts, and then it says, what's the work done by the spring as it returns to equilibrium? Work done. And I know someone's there. I'll get them in 1 second. Sorry, I'm just between screen. Okay, so we have to calculate the work. Now, who's that? Okay. Um, Now I'm gonna do what many of you did in your midterm, as you should, and you would do in your final. Like the question is, what's the work? What are my GD? Okay, so what are I hopefully you can see this is step 1 and step 2 so far. Step 3, in fact, let's do that. So the GDPs, the step 3 is okay. First of all, is F equals negative kx. Like that is the force exerted by the spring on the mass. But now the question is asking, what's the work done by this force as it brings the mass back to equilibrium? So also a step 3, a GDP would be that the work done in general by any force to bring something from one position to another would be the integral of force, right? So that's step 3. Is there anything else we need to know here? Step 3, no. Okay, so those are the two principles I'm going to use. Right, for this step, I mean, for this problem, those are the two principles I'm going to use, that the spring is exerting an elastic force and that the work done by any force is the integral of that force with respect to displacement. So I can go to step 4 now. Okay, so now I want to think for a second. Like, Okay, I just want to note, so I'm doing step 4. We're going to integrate the dot product of force with respect to displacement, right? Well, what I'm trying to say is that, and we're going to integrate from the initial position of the mass to the final position, which in this case apparently is equilibrium. So in other words, what I'm trying to say is if I'm trying to apply, if if my step 3 was F equals negative kx and definition of work, what I'm saying here, in other words, here, the work will be the integral from the initial position x naught, right, which happens to be 9 centimeters or whatever it is, some number of centimeters, to 0, right? Let's be careful now. So my step 3 was a triple equal sign, was the definition of work. In general, work is an integral from any one place to another, x1 to x2, any two, right, of the force dotted with displacement from place 1 to place 2. Like that's the general definition of work. Now I'm in step 4 and I'm applying that general definition to the specifics of this situation, right? So now I'm in like a double equal sign. And first of all, please note, like it's not a typo. Specifically, the values here, maybe I should have written it out in step 4, but I'm saying the first position is literally x naught, is that initial position given in the problem. And the final position is literally like x equals 0, equilibrium, because the problem told me so, right? I mean, step 4 now. And so I'm going to go like this. But remember, that means, oh, maybe this should have been another step 3, what I'm about to say. What does it mean to dot two vectors? It means to go like this, right? I mean, this is what we learned last week about work. Like work is the scalar product of the force and displacement vector components that are aligned with each other, that are parallel to each other, right? And so, by the way, just for clarification, maybe I should have even said in like if you were doing this in a final exam or something, maybe I should have even said in step 3 that in general, you vector A dotted with vector B equals AB cos theta, if you know what I'm saying. And stop me if you don't know what I'm saying. I'm totally looking at the chat. What a great question. Okay, so let me put back to this page. Okay, I'm going to finish that thought and I'm going to answer this question. But so I'm just saying now, well, I'll answer. So I'm saying work is the integral of the dot product of force with displacement. So now I'm starting to expand and apply, and I'm applying the definition of dot product to what I have here. But someone in the chat has asked, wait, is the integral like our new definition of work, or does it only apply when we have non-constant forces? What a perfect, like, someone's been paying attention kind of question. My answer is it is our new definition. From now on, if we define work to be an integral for all time, for all cases, that will enable us to handle all of the constant and non-constant force situations. Like, why I love that question, and I will move on after this sentence. Why I love that question is it's because we got to non-constant forces that we were compelled to think about calculus and to introduce this idea of the integral. Like, it's true that if all the forces were always constant, we wouldn't need this concept of an integral. Once forces change at all, we need the concept of the integral. But the concept of the integral is a general thing that continues to work even in the easy cases of constant forces. And the quick answer of why is you'll like, well, even here, what I'm doing here now, I'm about to do an integral, right? But look at that f that's in the integral. And don't be intimidated by the cosine theta. I'm about to get rid of it anyway, okay? But just look, I'm about to do an integral. The dependent variable is f. And f changes, that's why I'm doing an integral. But to answer the direct chat person's question, if f didn't change, If f were a constant, it would come out of the integral, right? And it would just end up being a multiplication of f times the integral of dx. The integral of dx is x, right? So, in other words, the integral reduces to the old definition when you're in a small interval case where the force doesn't change. I mean, this is why, okay, I won't go on, but you see, so we're doing the integral because it covers everything. Because when things are simple, when things are constant, the variable just comes out of the integral and then the integral goes away. So, I mean, it's so brilliant and beautiful. It makes me weep. Okay. So, but great question. Oh, got it. Okay. Okay. So, which means go on, yeah, Verbaum. Okay. So here we have this integral now. It might looks like there's more than one variable, maybe. It looks intimidating, but let's go step by step. First of all, as we noted in step 4, in this case, the x and the f are in the same axis. Like I'm not trying to make life, I'm just trying to practice, how we do these things. The angle between the two in this case, and this will always be true, what I'm about to say right now, in the case of a spring pushing a mass, like it will never be on an angle. Even if you turn the whole thing on an angle, as you actually do in the first lab of Physics 204, even if you took this entire apparatus and turned it 90 degrees, well, you would be turning the whole thing. So even there, the spring is along an axis and the displacement is along the same axis. So the theta is 0. So the cosine of 0, you might want to rush and put in the chat. What is the cosine of 0? Anybody run to the direct chat and get points. What's the cosine of 0? I'm going to move on as soon as I get 2 people in the chat. Awesome. Beautiful. Yes. Yeah, that's 2 people right there. Beautiful. Beautiful. Oh, that's a lot of people. And you're all getting points because it's direct chat. Isn't direct chat a wonderful thing? Yes. A bunch of people. Thank you. All of you submit for points. All just put 1. Right. That's awesome. The cosine of 0 is 1. So this integral is suddenly looking not that bad. Right? We have f dx, right? And now I'm going to the next page. That's just a Oh, so I'm literally saying what looked intimidating at first, like there's vector symbols, there's a dot product, but we define the like the vector symbols go away, not because we're ignoring them, but we're mathing our way through. And then the theta goes away, not because we're ignoring it, but we're like thinking our way through, right? So all of this stuff always, it looks complicated and intimidating at first, but you just go step by step and it starts to get cleaned up. So now we have this. Now, what is F? Okay, F is negative kx. That's Hooke's law. Okay, so now we have to integrate this. And you can see, so there literally is an x in the expression. That literally goes back to the direct chat part. Like, this is why we're integrating, because we actually have a function that is not constant, that depends on the independent variable. But it's not a bad integral, I think you'll agree. And this is representative. I'm not trying to trick you. The whole goal here is to totally understand what integrals are, why we set them up, how they apply to physics, et cetera, et cetera. But the actual in this context, once you finally get to an integral that you recognize or whatever, it'll be very recognizable and won't take a huge amount of the point here is not to do really elaborate things with like integration by parts or something like that. I mean, eventually that happens, but not here. Okay, so like the variable is x. The variable is x. So anything that is not x is a constant, right? K is just the stiffness of the spring, so it comes out of the integral. In fact, actually, I'm going to do this differently. Well, it, actually, let me no the negative sign also comes out, but let's do it like this. I mean, the negative sign can come out. Let's do it like this. You know what to do with negative signs, right? The negative sign I can get rid of by switching the limits of integration, right? Um, which I just totally did not do. Hold on. Okay. I'm just looking at the chat. Okay. So now let's pause for a second. Like I believe you know how to do this integral, or you remember. I think if you know how to do any integrals, I'm pretty sure you know how to do this one. Um, uh, One thing I'd like to remind the simplest, most fundamental integral of all. Oops, sorry. The most fundamental integral of all is just the integral of dx. And you know, in fact, I want to just ask, hold on. Say this just said, what is the integral of dx, like from 0 to x naught or whatever? In the direct chat, what is just the integral of just d, or put another way if you like this better, what's the integral of 1 times dx? What, close, wait, is that, I can't actually tell if I just got new answers. Oh, no, I didn't. I'm going to say, well, yeah, I don't want to write this down because I don't want to rabbit hole. I'm afraid of. Oh, good, good. Thank you. I'm gonna. If one more person does it, then I'm gonna move on. I got one. Good, good. I just got two answers. Three. Two and a half. Good. One answer was technically a little bit good. Yes, the answer of the integral of dx, the answer is x. Okay, and one person wrote x dx. Be careful about like when you integrate dx, you get x. Now, I just want to remind you of that. I don't know if you've memorized that or if you're doing a power rule in your head or what, but I want to kind of drum that in. That should be an anchor of our thinking about integrals. When we say the integral of dx is x, that really shows what the meaning of an integral is. That's a reminder that the integral symbol means add up. It means sum. That right? That was my emphasis from Monday. Integral means add up. So the integral of dx means add up a bunch of infinitely small segments along the x-axis. Like each dx is a little interval from one value of x to the next value of x, right? It's like each dx is like a delta x, except taken to the limit as delta x approaches 0. So to integrate dx means add up dx plus like an infinitesimal section along a meter stick plus an infinitesimal section along a meter stick plus an infinite. What do you get when you add them all up? You get the full meter stick. The integral of dx is x. Like that is not an accident. That's the definition of integrals, right? Now, if you want to do anything more complicated than that, what we have here is one step more complicated. We have the integral of x dx here. Now, how do we do this? I want to, hold on a second. I want to be clear that everything I said on Monday was about triple equal sign. Everything I said on Monday was about what the integral means and why we would set up, why we would write down, use the notation we do, and set up this thing called an integral to capture the idea of work. Everything I said on Monday was like, why work is the integral of force with respect to displacement and why it's written like that. Like why integrals are written like, dependent variable times d independent variable. Like it actually is saying something. An integral is always a continuous sum of products, right? That's what the integral is. Nothing I said Monday tells you how to do an integral. In fact, nothing I said Monday even proves that integrals necessarily are doable. Like if we just end with Monday, we don't know how to do one. We just know that's what we want. We want some process for adding up a bunch of rectangles under the curve, right? But what you learned in calculus, that is its own major discovery. Sorry. Whoa, I don't know why that thing is because every morning my board has even more coffee than I do. Sorry. Okay. What? Oh, you still remember? That's awesome. That's awesome. Okay. What the integral is, triple equal sign, is the continuous sum of products. How do we solve the integral? Well, we realize at some point later in calculus, after we after we invent the idea of the integral and say, boy, it would really be cool if we could do this thing, if we could chop up a whole region into an infinite number of infinitely small slices and add them all up. If we could just do that, we could learn so much. Then someone comes along and says, wait a minute, look, if we take our notation seriously, now what I've done here on the board is not a proof, but I think it is a vivid demonstration. Someone says, well, wait a second. If we take our notation seriously, that an integral is a continuous sum and derivatives are slopes in the infinitesimal case, slopes taken to the limit, right? If we had some y equals a function of x, if we were to integrate all of the slopes, if we were to take the continuous sum of products, so if we were to take a bunch of rectangles under the curve, and at the top of each rectangle, measure the slope of the curve at the top of that rectangle, and add up all of those slopes, right? Follow me. Like you put a ream on some, like someone said on Monday. You put a bunch of rectangles under the curve, which means to integrate. But now, if what we added up wasn't just the if what we added up wasn't just the widths of the rectangles, but in fact the slope of the curve at the top of each one of those rectangles, if we were to add up all of those slopes, well, just look at our notation. It seems like the dx's would cancel, right? It seems like the integral of dy dx would leave us with the integral of dy, and we just said 5 minutes ago that the integral of d anything is total anything, right? It would be the integral of all of the infinitesimal. In other words, if we added up all of those slopes and multiplied them by the infinitesimal runs, we get a sum of all of the infinitesimal rises. If you add up the sum of all the infinitesimal rises, you just get the total rise in the curve. I'm speaking a lot of words, but what is it saying mathematically? It's saying that evidently I don't know how to do an integral. I just want to be able to do an integral. But apparently, if I integrate derivatives, I get back the original function, right? I mean, if the function is y equals f of x, if I add up all of the slopes of that function, I get back that function. The integral of the derivative gives you the total value of the function between the two boundaries of wherever you're looking. I mean, literally, I'm saying, I mean, you know this. You know what I'm saying. I'm saying that given a function y, the integral of the derivative of y is simply just y, i.e., now pause on this for a second. I'm looking at the time. We've got a half hour. I'm saying Well, what did I mean by FTC? No, by FTC, I mean fundamental theorem of calculus. I'm saying the fundamental theorem of calculus is that if you take the integral of the derivative of a function, you get back the original function, i.e., the thing that all of you have known from the almost the first day you took calculus, i.e., integrals and derivatives are the backwards of each other. The integral is the inverse of the derivative function, right? In other words, what I'm saying is the integral is the antiderivative. And this is the fundamental theorem of calculus. Now, listen to me, please. I mean, I know you are listening, or what, but I'm telling you, this is another one of those physics moments, at least for me, and maybe hopefully for at least one of you. On the one hand, I'm saying the integral is oh my God, someone's here. Hold on. Sorry. On the one hand, what I'm saying is, no, I mean, entirely what I'm saying is the integral is the antiderivative. So, on the one hand, of course, if you are like most of you might well be thinking, well, of course, I can't believe Yaverbam just spent 20 minutes saying that. Like, I was forced to take 2 classes in calculus. If there's one thing I freaking know, it's that the integral is the antiderivative. In fact, that's what the integral is. It's the antiderivative. Like, hasn't he should have just been calling it the antiderivative for the last week of this class. But no, what I'm here to tell you is that's a double equal sign. When I learned the fundamental theorem of calculus, I had the reaction that maybe some of you might be having, or maybe you're having it and you don't even know you're having it. When they made a big deal to me, like, this is a fundamental theorem of calculus. The integral is the antiderivative. I was like, yeah, I know. What's so fundamental about it? It's so fundamental. Like, we've been using it for a month already. Like, why is this a thing? It's a thing because what the mistake I was making in my mind, and what I had been hearing my teacher say, and I'm not saying it was my teacher's fault. I mean, I have no idea. And I'm not saying anything that ever happened in your math class was your teacher's fault, whatever. But what it seems like to most of us is that right from the get-go, when someone says to us, like, what's an integral, or I'm learning integrals now, what we think is we're learning antiderivatives. Right from the get-go, unconsciously or consciously, many of us think that the meaning of an integral is a backwards derivative. So no wonder we don't know when or how or where to set them up. We don't know really what they're about. And it seems like we're going in circles all the time because we think, many of us, at least me, and I wasn't conscious of this, by the way. I just thought that the point was that integrals are derivatives backwards and just has a funny notation with this annoying dx in it. What I'm here to tell you is no, no, no. That's the difference between a triple equal sign and a double equal sign. What an integral is a continuous sum of products. What it is the rectangle thing, the Riemann sum thing. That's what it is. And we want it because we want to be able to look at the accumulated effect of some function through a region. Like until 2 weeks ago, all we ever had was Newton's laws, which I mean I love. Some of my best friends are Newton, obviously, but like all we could ever look at was forces acting on one point in space at one point in time, called a free body diagram. We just had force, snapshot, derivative, snapshot. But then we're coming along saying, wait, shouldn't it be relevant or helpful to be able to look at what a force does over a region of space? Like, what's the accumulated impact of force acting through an interval of space? What that is asking, what about if we were to make a continuous sum of all the force displacements throughout some large displacement? That would be an integral, right? So we say, let's invent this idea called an integral. That'd be cool. So we don't just look at forces in snapshots. We look at them through regions of space. That'd be cool, right? But then we're like, but crap, how would we do that? How can we even solve integrals? What do we do to get back to this problem, to get back to reality? Snap. Like, how can I even solve even this simple integral of k dx? The answer is, it turns out, double equal sign, it turns out as a discovery, which you can sort of see just the way we use our very clever notation. It turns out that when you integrate a derivative, you get back the original function. So apparently, to do an integral is to do a derivative backwards. So that turns out to be the technique. Now, a lot of integrals are a lot harder to do than others. So you take a whole course in it and you do all this practice in math stuff, but it's easy to lose sight of the fact that what you're usually doing in math is solving integrals, not setting them up. And so you're using the fundamental theorem of calculus, as I'm going to use now, to get back to reality. But I'm saying, to me, it was a really big breakthrough. I understood integrals a lot better when I realized, or when someone showed me or whatever, that an integral doesn't mean an antiderivative. Antiderivative is the technique for solving an integral. And so that's what I'm going to do right here. Now, and look, I know, again, I know a lot of you already know this answer. I mean, I hope that's why the homework was already assigned. I know you can get this. I'm just hopefully trying to show you what's going on. Anyway, so to do this integral of x dx, I'm asking myself, what is the function such that when I take its derivative, I get x, right? Like what would be the y, right? And so I want to do a power rule in reverse in my head. Like, right, like I'm going to stop me if you don't know what I'm saying, but I'm saying like, oh, if the power rule is, you know, actually just really quickly, just to make sure we're all on the same page. I'm looking at the time in the chat, in the direct chat. I'm just going to name a function. You give me the derivative. Don't give me the integral. Give me the derivative. So like if the function is y equals 3x squared, if the function is y equals 3x squared, what is the derivative? Like the derivative, like what is dy dx? If I give you y equals 3x squared, what is dy dx? And as soon as I get three answers, I'll move on. Awesome. Yes, that was really fast and correct. That's two people fast and correct. I'm going to wait for one more. So I'm going to say it one more time. Y equals 3x squared. What's the derivative? I'm going to wait for one more and then I'm going to move on. But the two people so far are correct. What that camera thing is bizarre. Y equals 3x squared. What is dy dx? Very okay. Yes, good. That's four people that, yeah, very good. So one person just like has a slight okay, couple okay. Oh, I will say okay. Most of these are totally right. And remember, by the way, if you got it wrong, there's a separate portal where you get extra points for having the guts to be wrong. That's not a joke. So don't. So be happy if you got it wrong. So the answer, I think there was one like typo. One person wrote six, but I think they meant what most other people wrote, which is 6x, right? If the function is 3x squared, you would take that power, multiply the whole thing by that power. So you'd multiply 3 by 2 and get 6. But then you would bring the power down 1. You'd bring it down to the power of 1. So you get 6x. Stop me if you don't know what I'm talking about. But right, I think that's the power rule. In other words, the power rule. Okay, wait. Okay. Like the power, just really quickly. Stop me if you don't know what that notation means. But yeah, a lot of you put it in. It's 6x is, I think, the answer, right? So you bring down the power and you bring down the power by 1. That's how you do derivatives, right? So then we're saying what I'm arguing just from this statement over here is if I want to do an integral, I'm literally going to do that in reverse. I want to produce the function that would have produced that derivative. I mean, I want to say so in reverse. Now I'm doing this fast. Well, maybe not fast as I should, because I think you've seen all this before. I'm just trying to put it in perspective now of what it means, why, and how it applies to physics. So, so if you do that in reverse, you you do the whole thing in reverse. If you what you were doing was multiplying by a power and then bringing back down the power to one, here you would bring the power up by one and divide by it, and you'd still have the a there. And you go like, and you'd evaluate, right? So that's what we're going to do here. That looks like Hebrew. Now, so I guess I'm just asking, if put in the chat then, what is the integral? What is the integral of x dx? Like if we do this power rule in reverse, if we do this power rule in reverse, the integral of x dx, I'm going to keep writing, but just put in the chat. What am I looking for here? I mean, I know you know because you did the homework, and a lot of you really did, which I appreciate. Like if I have this, I'm doing the power rule in reverse. Well, if I want to, so I want to raise the power one. I mean, yeah, I want to raise the power of one by one, and now I want to divide by that. Yes, good. I just saw a person in the, yes, I'm going to wait for one more. Like, what's the integral of x dx? I see one slight interesting attempt and then one correct answer. I want to wait for one more. What's the integral of x dx? Oh, I see another. Sorry. Yes. Good. Okay, wait. So there's a little struggling with this. All right, I'm gonna write, but two people are correct. I know you guys don't want me to slow you down, but I think it's, oh, sorry, and I did do this wrong. Sorry. This is supposed to be the other way. I think it's like this. Um, I think in the interest of time, like this is it's, in other words, you raise the power, it's x to the power of one. So I raise the power and I get x to the power of two, but then I divide by that new power and I get x to the power of two divided by two. It's literally just doing the derivative power rule fully in reverse. So I think, and then I evaluate. So I think, oh, oh yeah. Oh, the K disappeared. Sorry. Okay. I'm going to speed this up. We've got 18 minutes. I'm saying two things now, but getting back to the homework here. Oh, ooh, no, are you okay? But do you get it? I see the direct chat. Like, I'm fine if you're fine. Okay. Now I did a lot. Okay, that's fine. That's fine. Now, there's 17 minutes. I did a lot of work here. I'm trying to get back to the homework, obviously, but I want the reason I spent okay, to be clear, I just spent a long time sort of deriving this result, but now this result, of course, we're going to plug in numbers and get the answers from the homework, whatever answers we get. But the point is, this now, you didn't have to do all that work every single time. The first time you ever look at a spring, or you're ever asked about a spring, or if it's on the final exam or something, if you're asked about a spring, you show that you understand that work is an integral and you integrate the force of the spring, as I just did. Of course, it won't take you as long as it took me because I was like trying to explain every step, sort of with the assumption that maybe not everybody's calculus is perfect, right? But once you've done it, now this is, if you like, a memorizer. I mean, now you can rely on this anytime you see a spring in life from now on. This is the amount of work that the spring would do to bring a mass from a position x naught to the position of zero, to the equilibrium. And so I'm even going to go one step further and say, and then just plug in the right. So this is like a truism now. This is like a general thing. Um, this also means if I now go back to the lecture from not 2 days ago, but from last Wednesday, right? If this is the work, we said that any force that does a total amount of zero work around a round trip, any force that does no work around a round trip is called a conservative force. We said that about gravity a week ago. And I'm saying now, if you look, stand back and think about the physics or the math of a mass going back and forth on a spring is like it's unlike gravity in the sense that it is a variable force, but it is like gravity in that whatever it always wants to get you to a certain equilibrium position. And when you're coming toward the equilibrium position, the spring is doing positive work on you. Whereas if you're being pulled away from the equilibrium position, the spring would be doing negative work on you. So just like gravity, if you were to do a round trip under the presence of a spring, the total amount of work done, everything that would be transferred in would be transferred out. Every amount of kinetic energy that a spring could give a mass on the way in would be taken away on the way out, or vice versa. So springs store energy just like gravity does. So I'm just laying this out here in case the bell rings, right? Just like with gravity, we can define a thing called gravitational potential energy and say that the gravitational potential energy that an object has at a certain height above the ground would be the work that gravity would do to bring the object to the ground. I.e., so in other words, to cut to the chase, I'm saying just like gravitational potential energy is mgh, because mgh is the amount of work that gravity always does to bring you to the ground, like we proved that its path in a minute. Well, we just proved that the amount of work that a spring always does to bring you to the ground, to equilibrium, is 1 half kx squared. Therefore, spring potential energy is always 1 half kx squared. From now on, you can say that. I mean, again, just be careful. Because especially in the final exam, if something like this comes up, I mean, explain it the first time it comes up on the exam. If it does, when it does, then explain everything like I just did the first time. But then but then it's true, and then you can rely on it and stuff. So springs conserve energy just the same way gravity does. And this is also important. This is exactly the way Physics 204 starts with all this. So that's why I'm sort of trying to nail it. But now with 12 minutes left, I'm going to be like literal just homework man here. So all of that. Okay, so back to the homework. In fact, well, no, I'm not. Back to, so this is 2A. We were calculating the work done by spring. We've now said, well, the work done by spring from 0.09 to 0. So what we've now said is that work is 1 half K x naught squared. So K was given as this huge, this is a very strong spring, 30,000. Like in the lab, they would generally be in the hundreds, but whatever. And then x naught is given as 0.09, but we square that, well, hello, we square that. And we get 121.5 joules. Okay, so that's an answer. We haven't gotten an answer in a while. So that's the answer to question A, is the work that the spring does on the equilibrium, on the mass as it returns to equilibrium is 121.5 joules. Then it's question B. Calculate the kinetic energy. What's the kinetic energy of the block the moment the spring reaches the equilibrium? Well, assuming the whole thing was started from rest, right? Yeah, the whole block. Okay. So the whole thing started from rest. Well, the point is that work, this is now. Now we're applying all the things I said last week. Work always equals the transfer of energy. Whatever work spring does on the mass gives it kinetic energy. The initial energy of this mass was nothing because it started, at rest. So this total amount of work that it did all got converted into this gain of kinetic energy. The mass is 3. Well, I probably should. Okay, anyway. So multiply both sides by 2, and you get 243. So divide both sides by 3, and you get 81. Oh, sorry. It's not even, it's just, I'm sorry. It's just asking for the kinetic energy. So that's it. Sorry. The kinetic energy that it ends up with by the time it gets to the equilibrium is 121.5 joules. Like the work done is the transfer of energy. Please note, if the mass had started off with some other amount of energy, like if it didn't start from rest or we were measuring from a different plate, then the gain would be 121.5. But what it would end up with would be whatever it started plus that gain, right? Work is the transfer of energy is what I'm saying. But okay, so the answer, sorry, I went farther than the problem's asking. And don't do that on the, so the answer is 121.5 joules. If ever it asks like how fast it's going by the end, I just got the answer. Okay, but going on, so 2C, calculate the height. Oh, this is interesting. So now it says calculate the height that the block will travel up the ramp before coming to rest. Okay, so this is another conservative force net, right? There's no friction or anything. So the spring just bounced this block out. Now the block's got all the speed. Now it's got speed. It's got kinetic energy. It can start moving up a ramp. It will move up the ramp until it runs out of that kinetic energy, right? Until gravity does so much negative work on it that it takes away its kinetic energy and does what? Converts it into potential energy. So there's like actually different ways we could do this, but the most straightforward way is say, okay, here's a truism. Like if all of the forces doing work on an object are conservative, then the whole point of this potential energy idea, again, there's different ways you could do this. But once you introduce the idea of potential energy, we could say at any given spot, you have a total amount of mechanical energy called capital E. Like from now on, capital E stands for total mechanical energy. And that would be, by definition, the sum of all of your kinetic and all of your potential. If you add at any given spot that you are, if you add up all of your kinetic plus all your potential, that number will not change at any other spot. That's what conservative force means. Whatever it takes away of your kinetic, it's going to give back in the form of potential or vice versa. So as you move from spot to spot, from X value to X value, under the action of conservative forces, your total amount of kinetic and potential will never change. So that's a truism. That can be, by the way, you can say that's a step 3 GDP. Like total mechanical energy is conserved if and only if all the forces doing work are conservative forces. Okay, so but they are here. This is only involving gravity and spring. Like there's no friction involved. So at the top, so the total amount. Well, at the top of that hill, there will be no kinetic energy at all. That's where it'll stop. I mean, that's why it's done. Oh my God. Oh my God. What happened? So that'll be zero. At the top of the hill, it'll all be gravitational potential energy. At the bottom of the hill, there was no gravitational potential energy, but there was all this kinetic. Right? So at the top, and we figured out that number already, it was 121.5. So at the so what it's asking the height, right? So the height is 3 times 10 times h, i.e., h equals 125 over 30, which equals like 4.5, I guess. 4.05, sorry. So that's the answer. So the answer is 4.05 meters. Um, we have 4 minutes. We could do a couple more. We could do at least one more. It called it dy, but I called it h, whatever. Um, okay. So then the next question is E. What's the kinetic energy of the block when it gets back to the bottom of the ramp? Oh, sorry. I mean D. D. After coming to rest on the frictionless ramp, the block will, of course, begin to slide down. Calculate the work done by gravity as the block slides down. The work done by gravity is mgh. But we already knew, I mean, it's conservative. We actually already knew that on the way up. But so the work on the way down, and what that has to be is the 125, the 121.5 joules that it had. Like this is the whole point of energy conservation. The work on the way down must be the same as whatever work gravity did on the way up. And the work that it did on the way up was exactly what was required to get rid of all of that kinetic energy that the thing started with. So it's the same number again, not coincidentally. So then E, calculate the kinetic energy of the block when it gets back to the bottom of the ramp. It has to be so the question is, what's the kinetic energy at the bottom? And the answer is work is the transfer of kinetic energy. So the kinetic energy at the bottom has to be 121.5 joules. So then, and then it hits this. Okay, you see the point here. It's then going to hit the spring. It has a certain amount of energy. It's going to run out of that energy. That's the work that the spring will do on it. So the spring compression work will be again 121.5 joules. So then G, I'm sure it's going to ask what's the displacement of the spring. It's finally going to ask a question we don't know the answer. Yeah, how far will the spring be compressed as it stops block? Well, the point is, so we're asking what is X? Well, the work done by the spring must be 1/2 kx squared, so we could plug in all the numbers, but we know the answer. The answer must be 0.09 meters because that's where we got the 121 in the first place. Right? In the first place, we did 1/2 times 30,000 newtons per meter times 0.09 squared. So in other words, everything that was taken away has to be given back, or vice versa, if all of the forces acting are conservative. So We actually did a whole problem. Okay, so have a great day. So I'll see you. So have a great weekend. I'll see you Monday. But I'm here. I'm not going. I'm actually here if anyone wants to come by. But okay. Bye.
Thank you.
Thank you. Thank you. Okay.
Thank
Oh,
you.
Have a good
Have a
day,
good day.
Matilda.
thank you. Thank you. Thank you. Oh, and I got you direct chat. Yes, have a good one. And I see direct chat, final confirmation for the, got it. Excellent. I'm here. Yes. Okay. Have a good one. Okay. And I'm stop the
Hi,
share.
Professor.
Hi. Wait, let me stop the recording.